We will discuss El Nino over several podcasts, looking at many details, because this is a good example of how uh, ocean dynamics and atmospheric dynamics work together in the tropics to create this very well-known phenomena of climate variability. Okay, and this also relates to climate change in some sense that we will talk about. Okay, so what happens then during an El Nino? We had said that during normal times there is upwelling here, ocean is soaking up heat, and it's piling up warm water on the west. And for some reason, which nobody can explain you exactly what initiates it, the warm water begins to move towards the east. It's as if it was a loaded gun and somebody discharged it. This was kind of the analogy used by Klaus Wertke in the late 1970s. He was the one who coined the terms recharge, where warm water is accumulating, and discharge, when the warm water is released to the east. There are details because sometimes there are waves that go off and perturb the upwelling first before you can see the warm water moving east. So we will not probably get into those kinds of details, but there are incredibly good books and papers that talk about El Nino theories in detail. So since this is just a introductory course, we will just keep it to a minimum. But within the introductory course, we have already learned that if you have upwelling here, the thermocline would be pulled up here and pushed down here. But when the upwelling is reduced, the winds weaken, then the winds are not able to keep the warm water pushed to the west anymore, so they slosh to the east. They move the convection with them, as you can see the clouds here, and the thermocline then gets flatter because the upwelling and the Ekman divergence are reduced, or the Ekman divergence and the upwelling are reduced. So the nutrient supply and photosynthesis is reduced, fish die, seabirds die, Galapagos gets seriously affected, finches on the Galapagos are affected, and so on and so forth. So the Walker cell is perturbed, then the convection happens here, so you have anomalous rising motion here. I keep saying anomalous because these are deviations from what we expect in normal times, so you have to always remember that. Okay, so the pressure gets anomalously low over Tahiti and high over Darwin and the West Pacific, so there is a anomalous subsidence over here, and you can see now the Walker cell is almost completely reversed, with the surface winds having anomalous westerly component instead of the strong trade winds going easterly. Okay, and obviously if you move that much heat source around, the Hadley cell is going to be perturbed, the Walker cell is going to be perturbed, so everything related to the climates depending on Hadley and Walker cell also are going to be perturbed. Okay, we have kind of mentioned positive feedback already, but let's do that again. So here is the La Nina phase, where for whatever reason the trade winds get stronger than normal, so the upwelling gets stronger than normal, cold waters get colder than normal, and they extend further west because the strong trade winds will push them further west. More heat is taken up, the warm pool is a little bit more squished to the west and accumulates more heat because the cold waters are taking up more heat and moving it to the west, and poleward as well because there is Ekman divergence. But there is the subtropical cell which is accumulating this warm water between one El Nino and the next. There are details. For example, a La Nina can last for several years. Sorry. Whereas the El Nino discharges the warm water and typically happens over 9 to 12 months, sometimes lingers on into the next year. So it's as if it has a limited amount of water to spend, and when it spends, it goes back to normal. Okay? So we'll talk about the feedbacks in the next podcast, but you can see here that the strong upwelling actually outcrops the thermocline, brings it very close to the surface. The thermocline here gets deeper than normal, so the east-west tilt of the thermocline is increased during a La Nina. You increase the rainfall here, but and you can see the Walker cell gets a little bit stronger. Coastal upwelling gets a little bit stronger because along with the easterly trade winds, you have strong alongshore coastal upwelling. But the impacts around the world are not symmetric. El Nino does certain things, and La Nina sometimes does the opposite thing. For example, Indian monsoon, it tends to be drier during El Ninos, not all the time, but most of the time. And during La Nina, there tends to be excess rain, not all the time, but many times. So other regions may get a drought during El Nino, but not necessarily excess rain during La Nina. Okay, so the impacts are not always symmetric. Okay, that's something to remember. So the Walker cell, again, to remind ourselves, here is the Indonesian low that Gilbert Walker had looked at. There is the Tahitian high, the South Pacific high, associated with the cold upwelling winds. Why is it measured here and not here? Basically because the observations are made on islands. There was no observation set up on Galapagos, but data were collected on Tahiti by the French colonies that established there over in the maybe 18th century or so. And of course there was data available here. Okay, so during an El Nino, this becomes anomalously low and this becomes anomalously high. So the southern oscillation, as Walker called, is closely related to the El Nino, even though there are slight differences. Nonetheless, if you look at it as a section, this is like the zonal overturning circulation. Hadley cell was from the tropics to subtropics. Here you have rising motions over Indonesia, hitting the tropopause, going in both directions, sinking over here, and there is an Atlantic side as well. And this is the main Pacific Walker cell that relates to the El Nino. So you have sinking over the east, just like Hadley cell subsides over the subtropics, and you have warm waters converging into the deep convection. So convergence not only happens from the polar sides into the ITCZ, but over the West Pacific, it can also happen from the zonal sides, right? Westerlies and easterlies supply moisture to the deep convection. So this is what gets perturbed during the El Nino. So let's in the next podcast look at an animation and add details about how Bjerknes feedback. Jakob Bjerknes was the first one to talk about how ocean and atmosphere feedback and make the El Nino grow after the initial perturbation of the West Pacific. Okay?